In this video, we're going to talk about how linear differential equations can be used to model real-life systems. And specifically, we're going to look at the growth and decay models. As it says here, many physical theories involve either growth or decay. And these are some examples. Population growth, bacterial growth, I think they're pretty self-explanatory, right? Capital growth, or radioactive disintegration, which is same as decay. Now, some of these models can be described by the following initial value problem. So I'm going to move it up. Now, let me remind you that the initial value problem always comes in two pieces. So the first one is differential equation, and the second piece is the initial condition. So let's try to make sense out of what it says here and how it might be related to some of those models. So first of all, let's focus on the differential equation itself. Now, df dt, well, that's the derivative, right? And I'm going to make some notes here. So our independent variable in this case is variable t. Well, it's t because it's going to represent time. Independent variable. Well, and then capital F, that's what I chose here for the name of the function. But yeah, that's the function of t. Function of t. So what is this function? What is the meaning of this function? Well, this function represents certain amount at time t. So I'm going to write it down and then we'll try to relate it to the above examples. So function of t, it represents the amount at time t, if we describe it in general. So what kind of amount? Well, it all depends on the model that we're working with, right? If it's a population growth model, it represents population, right? Number of people at certain time t, at certain year, and so on and so forth. So if it's bacterial growth, well, it represents the number of bacteria at certain time t, and so on and so forth, right? Capital growth, amount of money at certain time t. So that's the meaning of this function. Now, going back to this differential equation. As we already said, the left-hand side, or as we can see it, the left-hand side of this differential equation is the derivative, right? That's the first order derivative. Well, what's the meaning of the first order derivative? Remember, it represents the rate of change. So that's rate of change. Well, and that's where that growth and decay is kind of like hiding behind, right? The rate of change of growth or decay. And what is it equal to? So on the right hand side we have k, we haven't defined that yet, we'll make a note in a second, times f. Well, that f is that same function. Now, what is k? K is called a constant of proportionality. I'll write that over here. Maybe I'll change the color. That is the constant of proportionality. Okay, so constant of proportionality, it means that the left-hand side, which is rate of change, is proportional to what? Well, it's proportional to this function. So in other words, this differential equation is going to be used for the models where we can say that rate or rate of change is proportional to what? To the number or the amount of something, people, bacteria, radioactive substance at time t. And we'll do examples, but we'll observe that within the examples. But in general, we can say the following: if k, so k can be either positive or negative number. When k is positive, then for that model, or for that situation, the model will represent growth model. So growth. And then when k is negative, that will describe model that has a decay. Now, this will make a little bit more sense when we look at the example. But before we do that, let's now talk about this initial condition. What's the idea of the initial condition within the initial value problem? Well, remember, as with the examples, initial value problem examples, the initial condition is always given to us with specific values, right? So t sub 0 and then f sub 0 here representing specific values. So t should represent specific time. Specific time. And for that, I will say specific function value. And once again, the function itself represents here certain amount or amount at certain time, amount of something, number of people, number of bacteria, and so on and so forth, so on and so forth. And if we put it all together, then we can say that, put this all together with some examples, I can give you kind of like some sentences that once you read them, you should recognize that those models are the ones that can be described by the following initial value problem. So here's an example. The rate at which the population of a certain community grows is proportional to the number of people present at time t. So first of all, the keywords here are rate, right? Proportional. And now as I underline those keywords, I am looking at that differential equation. Rate, the left-hand side, is proportional. That's key. That's k, constant of proportionality. Proportional to what? To the number of people present at time t. But the number of people present at time t, well, that's the function itself, right? Represents the amount at time t. So notice how, as we look at keywords, at all those keywords, we can actually recognize the equation itself. Let's try it again with the next example. So it says the rate of disintegration is proportional to the amount remaining at time t. So rate is another keyword, right? At the left-hand side, that derivative, first order derivative, is proportional, k, to the amount remaining at time t. So probably like for the specific example, it should say the amount of radioactive substance remaining at time t. So once again, with those few examples, I want to show you what you want to find within the problem that you're trying to solve, so that you know you have to go with this initial value problem to solve that. So that, that wording should be present. And then finally, so we're basically ready to do examples, but just as an extra information here that you might need and find helpful as you do some specific examples is information about half-life. So you can also come across half-life questions, and here's just a few notes about half-life. So what is half-life? It says here in physics, the half-life is the measure of stability of a radioactive substance. That's kind of like a general definition. So half-life measures stability, but how exactly it measures stability? But now here's the more kind of like a straightforward definition of half-life. So it says that the half-life is the time, so that represents time, that's t, right? It's time. What kind of time? Well, it's time that it takes for 1/2, which is same as 50%, of the atoms in an initial amount to disintegrate or transmute into the atoms of another element. So one more time, half time represents time that it takes for half of the atoms to disintegrate or transmute into some other other atoms, right? And kind of to connect those two together, we can read this last note. It says that the longer the half-time of a substance, the more stable it is. That's how it measures the stability. More time it takes for half of the atoms to disintegrate or transmute into some other other atoms, more stable it is, right? So that's how we think about it. Now let's try to describe that using mathematical notation. So if we continue using function f, by the way, you can rename that function. For a specific example, you can use different letters. So if function f represents the amount of radioactive substance remaining at time t, then using the half-life idea, we can put together this equation. So function value at t, that is half-life, at this time that represents half-life, equals, well, take the initial amount of that radioactive substance and divide by 2. So that is mathematical notation that corresponds to, well, the definition of half-life, specifically that second bullet point, kind of like this straightforward definition. So that's how you can connect things together using mathematical notation if you're doing an example with half-life.